Let's continue with alcohols. Dehydration of alcohols. To dehydrate is to lose water. Okay, so it's loss of H2O. An organic molecule loses the elements of water, which could be a H and an OH. Of course, alcohols have general formula like that. You could have a primary alcohol that can dehydrate. You can have a secondary alcohol that can dehydrate, or a tertiary alcohol that can dehydrate. Usually dehydration mostly occurs by E1, but for primary alcohols they will do E2. Okay, no intermediate is formed for primary alcohols. This is a primary alcohol again because the carbon bearing the leaving group is bonded to one other carbon or one R group, so it's primary. So OH are not good leaving groups. Remember we said leaving groups must leave as weak bases. That's very important that leaving group leave as weak bases, and we talked about factors that make them weak bases, including electronegativity, resonance stabilization. Okay, resonance stabilization. We also talk about size. We talked about inductive effect. Those are the things that will make the leaving group a good leaving group and a weak base. So if you assume OH leaves, for example, assume the OH drops off. What are you gonna get? You're gonna get a primary carbocation, which is bad. You don't want to form primary carbocations. And also you're gonna make OH minus, which is obviously a hydroxide, which happens to be a strong base. Okay, so this is a bad leaving group. So in order for OH to leave as a weak base or weaker base than OH minus, we use an acid catalyst. So the acid catalyst helps it to leave. So we use a lone pair on the oxygen to accept the proton of the acids, because acids are proton donors. You get oxygen to be positively charged. Now this can leave as water. Remember we said that water is a good leaving group. It can leave as water, but not yet, because if it leaves right now, you're gonna again make a primary carbocation which is unstable. That's why primary alcohols don't go through formation of carbocation before you form the pi bond by E1. That does not happen because the primary carbocation formed is highly unstable. Stability of carbocation is primary, secondary, then is tertiary, secondary, then primary. Tertiary is more stable than secondary, secondary is more stable than primary. So we usually don't want to go through a mechanism that will give us a primary carbocation. So what is the alternative of making a diabond? Because this would have made a diabond if a base like water would pull out the beta hydrogen using the lone pair on oxygen. If you pull out that, you would have made a diabond, right? I mean that if you have this primary carbocation and you use water as a base by E1, because water is a weak base, that will go there and you make a double bond. Where does the water come from? It might have left from this step here. But anyway, we are not thinking E1 because again, this is primary carbocation that is not stable. So we take the same molecule, this molecule, and form the double bond as the water leaves. That mechanism that avoids formation of carbocation is E2. And it's E2 because you're making a double bond. Okay, so you just take out the beta hydrogen sitting on a beta carbon, which is the carbon bonded onto the carbon bearing the leaving group. So take this out using the weak base. Okay, what is a weak base? Remember, it's not negatively charged. Take it out, make a double bond as this one leaves. That's what's being shown on here. So the water uses its lone pair of electrons on oxygen to take out the beta hydrogen. You make a double bond as this leaves, so you make your product. So you would have made it by E2 and not by E1, which would have gone through a primary carbocation intermediate. So no intermediate is formed for primary alcohols, and we also go through E2, not E1 for primary alcohols, because we are avoiding formation of primary carbocation, which is unstable. Dehydration, removal of elements of water by using secondary alcohols. Now, remember I told you dehydration is removal of elements of water. We are losing water in the mechanism. Here we lose water, so you're losing H2O. So it's dehydration. So if you have a secondary can do E1 or E2, whichever it needs. Now that's just gonna be probably dependent on the strength of the base to define whether you're going E2 or E1, and it's also gonna be dependent on anti-periplanar hydrogen atom, because E2 requires that the beta hydrogen to be removed, be 180 degrees in orientation to the leaving group. Okay, if it's not, there's gonna be a rotation, then it will happen. There will be a sigma rotation, sigma bond rotation, then you remove the beta hydrogen. Okay, so let's look at the secondary alcohol. So let's say you have this alcohol. Again, OH is not a good leaving group. Dehydration mechanism by E1 or E2 for OH most likely is gonna need an acid catalyst. Okay, that makes OH a good leaving group to leave as a weak base. So you get this the second hydrogen attached, so oxygen is positively charged, and now the water can fall off, and now we can make a secondary carbocation which is acceptable. That one can work. We can use that for the mechanism compared to the primary here that we did not want. So now the secondary carbocation can lose its beta hydrogen. You know, here as the water fell off, it's just gonna be this is a plus charge, it's gonna be a byproduct here. So that byproduct of water that fell off will be used as a weak base to take out a beta hydrogen, and then you get your product. That's by E1. This is E1 mechanism. Okay, from here it's E1, but you can go E2. From here you can go E2, where the hydrogen that is 180 degrees to the leaving group can be taken out. So all I need is H2O to take out this hydrogen. You make a double bond, and I would also push this arrow at the same time. I get the same product. So either you're gonna go E2 or E1 to make the same product for a secondary alcohol. If you don't remember, the secondary alcohol has two R groups bonded to the carbon bearing the leaving group. Zaitsev rule also applies, especially for dehydration. Okay, so always applies with dehydration. Remember what we said Zaitsev rule is: in reactions where you form double bonds, the most substituted double bond will happen to be the major. So let's see how this is happening. Again, it's still dehydration. Make OH a good leaving group. You're activating it. You want it to fall off as water, not as OH minus. So this falls off. Guess what you're making? As that fell off with the bond, you get a plus charge here. That's a tertiary carbocation. Now, you're also going to get H2O that fell off as a leaving group. The H2O that fell off can come back as a base to take out this hydrogen. That's the beta hydrogen, right? Sitting on a beta carbon, which is bonded to the carbon that had the leaving group that left. So take out that hydrogen, use the bond to make a double bond. So if you do that, you get this product. Now, what if you use the same carbocation, but this time you're taking out this beta hydrogen right here, because you know you have this one, you have that one, and that one. Those are 3 beta hydrogens. Of course, here you have 3 hydrogens, 2 hydrogens, but I'm just showing one of those sets that will be taken out. So this and these are similar. Both of them are sitting on CH3s. So I showed here taking out that, so it's the same as taking out this. You'll get a double bond here, which if you flip, you're gonna get this product. Anyway, so let's use our water to take out the other different beta hydrogen. You make a double bond in there, you're gonna end up with this product. Again, to be clear, you have a positive charge, you have a hydrogen, you have H2O that fell off during the formation of this carbocation. So you take out the hydrogen, make a double bond, you end up with this. Of course, the water, after it takes out the hydrogen, it's gonna form hydronium ion. That's inorganic. Our concern are these 2 organic products. Now you have a CH2 here, you have an R group, so this is di-substituted. Okay, and this one is tri-substituted. Tri-substituted. Okay, tri-substituted. So according to Zaitsev rule, this tri-substituted will be the major product. It's tri-substituted because if you cut the double bond, you see you have 3 R groups directly bonded to the alkene. So that's the major Zaitsev product. The other one is minor, and the name for that, I think it's not shown in your book, is called the Hofmann product. The Hofmann product is just the opposite of Zaitsev product, which means it just has a less substituted double bond named after the scientist called Hofmann, like this one was named after the Russian scientist called Zaitsev. Okay, how do alcohols react with hydrogen halides? Hydrogen halides are like HCl, HBr, of course HI. Definitely, like we've shown, whenever you have an alcohol, if you have an acid, then the oxygen will be activated so that the OH leaves as water, right? So the alcohol here is reacting as a nucleophile, the acid plays the role of an electrophile. So the oxygen takes out the hydrogen, the leaving group leaves. The oxygen is now gonna have a positive charge if you do the formal charge calculations, and now you have a Cl minus, and then now this can fall off. Okay, you get a tertiary carbocation, and then the Cl that was removed from this step can come back to attack, and that's how you make alkyl halide. So hydrogen halides are acids, so they will protonate the OH group. That's what I've done here to make water, which is this group here. Once it leaves, you're gonna get H2O as a byproduct, which is an excellent leaving group. Yes, that's the excellent leaving group is gone. However, the halide atom is nucleophilic, so we get nucleophilic substitution, which is what we have here. It's SN1. This is the halide that fell off from HCl. It comes back to attack as a nucleophile. Okay, it attacks the carbocation. Because you have a carbocation, we do substitution by SN1. You end up with the Cl, you started with an OH, you've substituted, that's nucleophilic substitution. Elimination will not likely happen, which means if you have a carbocation and you have the beta hydrogen, Cl is less likely to do elimination. So this is less likely to happen. Okay? Usually what needs to happen is the SN1. And you have several examples here. Okay, so if you have a tertiary alcohol reacting with HBr, use the lone pair, take out the hydrogen that leaves, okay, you get a good leaving group ready to fall off, which is water. When this falls off, okay, remember here, once you took your hydrogen, Br minus fell off. When this falls off, you get a carbocation, and then the Br minus that fell off from step number 1. See, step number 1, protonation of water, as Br fell off, you get Br minus. That Br minus will come to haunt or attack the carbocation, you get your substituted product. Now, because you started with OH, you end up with Br, that's already a substitution reaction. Okay, but what type of substitution? We went through formation of a carbocation, in this case is tertiary, so we are thinking SN1, because SN1 and E1 go through through carbocations. So similarly, here the oxygen will take out the Br hydrogen, okay, then you get hydronium, which will fall off, and then of course the Br fell off from the first step. So from here, when water leaves, you're going to get a carbocation, which is secondary, and H2O. The Br that fell off from step number 1 comes back to attack the carbocation using its lone pair. You've substituted OH with Br. Now, alternatively, you can do SN2, where the H2O will leave as the Br attacks without formation of carbocation. See, that's concerted reaction. That will still give you this product after formation of this complex that can go through SN2 to give you the same product. Okay, now the problem with primary alkyl halides, because this was the case with secondary, the problem with primary is that you don't want to form a carbocation intermediate like we said before. So SN1 will not happen, because if this falls off as water, you're gonna get a primary carbocation which is not stable. So we need to do SN2, and to do SN2 with primary, one always requires a metal catalyst, where the oxygen will attack the zinc. Okay, so you're gonna get a complex of zinc chloride with the oxygen positively charged, and then you will have the Br of the acid come to attack from the back. Okay, it attacks from the back as this leaves, this complex leaves, you get the substituted product. So basically, for primary alcohols, just simply switch the OH with the alkyl halide of the acid. That's a shortcut to avoid complex mechanisms down here, which I think are beyond your scope. All right. So next we'll talk about other routes to alkyl halides.